Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're talking about thermodynamics, the first law specifically for a closed system, the famous delta U equals Q plus or minus W, heat and work. This is a question by UNSW, and it reads like so. Steam, having a mass of 3 kilograms and initially at 2.5 megapascals and 350 degrees Celsius, has 2,460 kilojoules of heat removed at a constant temperature until the quality is 90%. A. Show the process on a PV and a TS diagram. B. Determine the pressure when dry saturated steam exists. And C, the work done during this process. So let's start by analyzing the problem. We have steam, so we're going to be using steam tables. This is not an ideal gas, so therefore we need the steam tables to be able to grab the properties. We have the mass, so whenever we get things in respect to kilograms, we can multiply by 3 to get the full amount of energy. And initially at 2.5 and 350. This screams superheated, but we're going to be sure, right? We have 2460 kilojoules leaving the system, right? Removed from the system. So we have heat going away from my steam. This is important for two reasons. One, we know it's going to be our second state is going to have less energy than the first state, but also this is in kilojoules, and we're giving the mass in kilograms, right? So note that when we go to the steam tables, we're going to find information in kilojoules per kilograms. So that means we need to multiply that by 3 so that we can get kilojoules and relate back to the information we were given. This happens at a constant temperature. Obviously, this is super important. And the quality is 90. So what do we know about the second state? We know two key pieces of information. The first piece is that quality is 90%. The second piece is that the temperature of the second state is 350 Celsius because it has to be the same temperature. We need to draw this on a PV diagram, TS diagram, and do the pressure. Okay, when does dry saturated steam exist? What does that mean, right? So dry saturated steam is a fancy way of saying saturated vapor. Because if you recall, the definition of saturated vapor is precisely vapor in which you don't have any droplet of liquid whatsoever. And as soon as you remove the first amount of energy, you're going to see the first droplet of water forming. Okay, so it's the same thing as saturated vapor. And then we need to calculate the work done in this process. Note that we have the key to finding internal energy, and we're given the amount of heat, so we can use this famous equation for a closed system to find work with it. Okay, so let's get started by first quickly drawing what's going on. We have our first state here, state 1. State 1 has water inside, steam specifically, and we know it is at 350 degrees Celsius, and we also know it's at 2.5 megapascals. And then as we go from steam from state 1 into state 2, we know that we are removing energy in the form of heat. So heat is leaving my system. Okay, and then in the second state, we know we have 350 because this is an isothermal, and we also know the quality is 90%. So that's all we need to know to be able to define the second state, and we can grab property for both states. Okay, so what I'm going to do is I'm going to first check to be sure this is superheated. All right. Then I'm going to grab my internal energy for this state. To be able to draw this, I'm going to need to grab the pressure and the specific volume for this state 2. And then I'm going to need to do the same thing for the other state. Okay, so on both states, I'm looking for specific volume, I'm looking for pressure, and I'm looking for internal energy. And I'm also looking for the entropy, right? The entropy. Because entropy is required to be able to do our TS diagram. So let's draw our game plan here. Game plan is check status of state 1. It's probably a better word for that. State 1, grab specific volume, entropy, internal energy, and pressure for state 1. Grab same thing for state 2, and then finally answer questions, because at that point we'll be able to do answer all the questions that were being asked. Okay, so let's check the status first. I have a table here, saturated water temperature, and I'm at the pressure of 2,500 kilopascals, which is exactly the same thing as 2.5 megapascals, which is what we have. Okay, and we can clearly see that the temperature, saturated temperature, is 223. So because our temperature is 350 and is greater than 223, we can be sure, 100% sure, that this is superheated. So I can give a tick here and say this is a superheated state. So therefore I need to go to my superheated table, and here on my superheated table I'm going to look for my 2.5 megapascals and for the 350, and I'll be happy to grab the specific volume, the internal energy, and the entropy. Okay, so we can grab all those three. And then the pressure we always had. So we needed pressure, we already had that, so we don't need the pressure on this one, only on this one. All right, so for state 1, all solved. For state 2, I need to go to the saturated temperature for saturated water table for temperature at 350, because that's the temperature of our second state. And here I need to look for the specific volume, for the internal energy, and for the entropy. And to do that, because we know it's 90 quality, we know that 90% of what we're looking for is coming from here, and the remaining 10% is coming from here, right? So all we need to do is some simple math to be able to grab all the three properties we're looking for. So in this case here, we're going to do specific volume of state 2 will be 90% of 0.00886 plus 10% of 0, I might do this on the bottom, so plus 10% of 0.001741. Okay, and that gives me that specific volume 2 is about 0.0081. And that is meters cubed per kilogram. Beautiful. Now, for internal energy, same deal, okay? I'm just going to change colors. So I'm going to get 10% of this and 90% of this. Or if I want, I can also use the difference between them, right? And make my life a bit easier. So whatever rocks your boat. So if we want to do the second one, all you need to do is grab the fluid one. So 1642.4 plus 90% of the difference, okay? Which is mathematically equivalent. So 775.9. So U2 ends up being 2,340.71. 2,340.71. That is kilojoules per kilogram. And just a reminder, we don't want this kilogram here, right? We want to get rid of that to be able to relate the other property that we have. Last but not least, same thing, 10% of this guy, 90% of this guy, or I can just use the difference. And if I choose to use a difference, what I'm looking for here is 3.7788 plus 90% of 1.4326. Okay, and therefore my entropy 2 ends up being 5.0681, and that is kilojoules per kilograms per Kelvin. Okay, once again, I don't want this.